look at it at their own time. So what we've been doing, we worked on the probability of or when we had this joint event. So for this joint event, we have probability of A, and you just had to add it to probability of B. So this is for disjoint or mutually exclusive event. So what we're going to be working on today is when we don't have disjoint event, when we actually have events that have an intersection. So when you say intersection, we're talking about that they share something in common. When we say share, it is saying that both of the outcomes could occur at the same time. So we're going to go ahead and look at this Venn diagram. So if you look at the Venn diagram, it's a little bit different from the other Venn diagram that we saw when it was disjoint. Because when it's disjoint, you have one outcome, but then you have another outcome. But if you look at it, they're disjoint. They don't overlap each other. So today we're going to be working on the case when we do have an overlap. So usually the overlap is this portion over here because that's where they overlap or that's where they share or intersect. So when they overlap, what we have to do, we have to adjust our formula because we can't do the probability of A and add it to probability of B because that would give us an answer that doesn't represent that doesn't represent what we're looking for. Could kind of imagine if we want to find the probability of A, you take this probability and then you add that to the probability of B. But when you add that to the probability of B, if you kind of notice that middle portion, we counted it double. So since we counted it double, what we have to do, we have to just subtract this portion right here. And that's what this formula is saying. It is saying you get the probability of A or B, you have to get the probability of A, then add it to the probability of B, but you have to subtract it by the probability of A and B because we double counted this middle portion. Cool. All right, so that's what that formula is saying. If you look at the bottom formula is also saying the same thing. The only thing different, instead of putting or and add, I'm putting the notation. So instead of putting or, I'm putting the symbol for or, which is the union. And for add, instead of putting and, we're putting the symbol for add, which is pretty much the upside down U. So that's the formula we're going to be working on today. All right. Any question in regard to the formula? All right. So let's go on and let's do this very first problem. So for the very first problem, I say use the information for event A and B. We have probability of A is equal to 0.4, probability of B is equal to 0.3, and probability of A and B is equal to 0.1. So it says find the probability A or B. So the key thing that they give me that make me know that we have something that's not mutually exclusive or not disjoint is this over here that they give me the probability of A and B. Because if it would have been a disjoint event, the probability of A and B would have just been equal to 0. But since it's equal to something else other than 0, I know that this is not a disjoint event. I know that pretty much they share something in common. So that's why we have to use this formula. So we're going to say probability of A or B is equal to the probability of A, but they already told us probability of A is 0.4. Then they tell us the probability of B is 0.3. And then lastly, they tell us the probability of A and B is minus 0.1. So if you go ahead and do 0.4 plus 0.3, 0.4 plus 0.3 would give us 0.7. And then if you do 0.7 minus 0.1, you do, well, you get 0.6 or you get 60%. And that's it for that last problem. Any questions for the last problem?
Wait, is that a negative 0.1?
Yeah, negative 0.1. Okay, if you look at the formula, it says subtract the probability of A and B. So that's a negative 0.1.
Okay.
All right, any other question? All right, so let's move on to this problem over here. So for this next problem, it says about 20% of movies coming out of Hollywood are comedy. Warner Brothers have been the lead studio for about 9% of recent movie, and about 2% of recent movie are comedy from Warner Brothers. So it said, let's C denote the event a movie is a comedy, and W denote the event a movie is produced by Warner Brothers. So part A says, write the probability expression for each of the three facts given in the first sentence of the exercise. So when we're talking about the facts are just the percentage. So we get 0.20, we get 0.09, and then we get 0.02. So those are the three facts that they give me. So what we want to do, we just want to use the proper notation to label them, to say what is the 20%, what is the 9%, what is the 2%, what does it represent in the problem. So let's first do 20%. So for 20%, what does the 20% represent? If you want, you can put it on the chat.
Movies coming out?
Well, which type of movies?
Or comedies?
Comedy. So we'll put C here for comedy. All right, what about the 9%? What does the 9% represent? Cool. Warner Brothers, perfect. So you put W. And lastly, what does the 0.02 represent? Yeah, comedy and Warner Bros. Perfect. All right. So that's it for part A. So part A, we have probability that the comedy is 20%. Probability it was produced by Warner Brothers is 9%. And the probability the comedy and was produced by Warner Brothers is 2%. Good. So let's do B. So for B, it says, what is the probability that a movie is either a comedy or produced by Warner Brothers? So right here, the keyword is or. That's telling me we're going to have a U. So if you look at it, it says we're doing a comedy or it was produced by Warner Brothers. So put C, U, W. Any question where we're going to find the probability that the comedy or it was produced by Warner Brothers? Okay. So let's go ahead and right now we're going to write it as a notation. So we're going to find the probability that it's a comedy. We're going to add it to the probability it's produced by Warner Brothers. And we're going to subtract it by the probability it's produced by, well, it's a comedy and was produced by Warner Brothers. So let's go ahead and find that probability. So the probability of the comedy, they already told us, is 20. The probability was produced by Warner Brother, what we already know is 0.09. And then we subtracted by the probability of the comedy and produced by Warner Brother, which is 0.02. So if you do 0.20 plus 0.09, that's going to give you 0.29. And then if you subtract it by 0.02, it should give you 0.27. So you get 0.27 or 27%. Right. And that's it for that first problem. Any question in regard to how we did that problem?
Oh, is the keyword or, does that automatically means that it's joint? Or
Yes. So once it says the or, that means you're finding a joint probability. So that means you want to use one of these two formulas. So yeah, so the keyword here is or. Good. All right, so let's scroll on down to the next problem. All right, so for the first problem I gave you, it was if they're giving you percentage. So in this next problem is that they're not gonna give us a percentage, but they're gonna give us the actual amount of people that fall into each category. So let's go ahead and read this problem. So it says in a school of 320 students, 85 students are in band, 200 students are in sports team, and 60 students participate in both activity. What is the probability that a student is involved in either band or sports? So once again, there's your keyword or. So if you look at this problem, they're telling us about two different type of students. So they're talking about students who are in sports team, but they're also talking about students who are in band. So we're gonna find sports, but we're also gonna do band. And if you kind of notice for this one would not be a disjoint event. The reason why it's not a disjoint event because you could be in a sports team and in band. They're not mutually exclusive. Like you could be in band and in a sports team. So how many students do I have that participate in a sports team? Cool, 200. How many students do I have that are in a band? Cool, you're on fire, Kimberly. Okay. So if you notice right now we have 285, but that's not a probability, that's a frequency. If I want to make it into a probability, what I have to do, we're going to divide it by however many total students there is in this school. So how many total students do they tell us are in this school? Yeah, 320. Good. All right, so we have 200 out of 320 for sports team, and we have 85 out of 320 for band. But if you also notice right here, they said 60 students participate in both activities. So that means we have 60 students who are in sports and in band. So you put 60 out of 320. All right. Any question about any of those notation that I have so far? All right. So let's go ahead and do the formula. So the formula said you get the probability of band or sports is equal to the probability, the probability they're in a band plus the probability they're in a sports team subtracted by the probability they're in band and a sports team. So all I'm gonna do now is just substitute everything that we found. So we found that for a band, they're 85 out of 320. For a sports team, it will just be what you call it, 200 out of 320. And then you subtract it by however many students you have that are in band and a sports team, which is 60 out of 320. So if you do 85 plus the 200, that give you 285. And then if you do 285 minus 60, that should give you the 225. And you divide that by 320. So then what you want to do, you just want to divide that out. So if we do 225 divided by 320, you should get 0.703 or 70.3%. And that's your final answer for that last problem. Any question for that last problem? All right. So for this last problem, there's actually another way that you could do it. And the other way that you could do it is by using a Venn diagram. So I'm going to show you how to do it using the Venn diagram. All right, so let me make some space here. All right, so that's my Venn diagram. So I'm going to say this is how many people participate in band. And I'm going to say this is how many people participate in sports. So for this one, what you want to make sure that you do, you first always want to put the intersection or the middle portion, because the middle portion could be vital for this problem. So you always want to put what is this middle portion worth. So if you remember, that middle portion represent how many people are in both band and in sports. So how many people do we have that are in band and in sports?
60.
Yeah, 60. So we put 60 over here. So the intersection always go in the middle. Any question for the intersection? All right. So up next, what you want to go ahead and do, I'm going to go ahead and do band right now. So if you look at it, I already have 60 people who participate in band and sports. So that means for this area in the outside are people who just participate in band. So they don't do sports, they purely just do band. So if I have 60 people who do band and sports, how many people just do band if I wanted to add up to 85? Yeah, 25. They put 25 over here. And the way that you get that, you just do 85 minus the 60. And that's how you get the 25 for over here. Okay, if you do 25 plus the 60, you get 85. All right. Any question on the 25? All right, so let's do sports. So when we found the 60 are 60 people who participate in band and sports. But now what I want to do, I actually want to find people who yet participate in purely sports. So we don't want people who do band. We want people who do purely just sports. So if I know 60 people do band and sports, how many people only do purely sports?
One, 140.
Yeah, 140, good. They do 140. Because you have 200 people who participate in sports, but 60 of them participate in sports and band. So if you do 200 minus 60, you get 140. So that's where the 140 come from. All right. Everybody get how we got 25, 60, and 140? All right. So up next, we're going to go ahead and we're going to go ahead and find the probability that they participate in sports or band. So we have 25 people who yet participate purely in band. So you put 25. You have 60 people who participate in band and sport. So you add that up. And then you have 140 people who yet participate in purely sports. So if you add this up, 25 plus 60 plus 140, you get 225. And you divide that by 320. And if you look what we got over here, this is exactly the same thing as we got over here. And that's it. Any question in regard to the last portion? So for this one, you could do it either way. You could either use the Venn diagram or you could just use the actual formula. Both of them will give you the same answer. So it doesn't really matter which of the two you use, as long as you use it correctly. All right. So that's it in regard to the general addition rule. So what we're going to go ahead and do next, we're going to go ahead and do the multiplication rule.
Can we use either formula?
Yeah, you can use either formula. Like
Okay.
both formula will give you the same answer. All right. So up next we're gonna do 3.2. Well, sorry, 13.2, not 3.2. And 13.2, we're gonna get into something called independence and also the multiplication rule. So when we talk about independent just means that one event is not going to influence the probability of the second event. So kind of think about it like flipping a coin. If I flip a coin, if the first time I flip it and land on head, what's the probability that the second time I flip it, it gonna land on head? Well, it should still be 50% because it's not gonna affect it. Every time I flip a coin, I know it has a 50-50 chance that it could land on head or it can land on tail. So every time I flip a coin, I know it's gonna be 50%. So that's why I know it's independent. Because one event doesn't influence the probability of the second or the third or the fourth event of occurring. So if it is dependent means that the probability of one outcome is going to influence the next outcome of occurring. So if I know one event is occurring, it's going to change the probability of the second outcome occurring. And that's what we call a depending event. All right. So up next, we're going to go ahead and we're going to go ahead and just look at these different examples. So for this one, say John wrote a 6 on a number queue. So let's draw a number queue. So number queue is just a dice. So No. So John rolled a 6. And then he said he flipped a coin, and when he flipped the coin, he got heads. Well, we can't really do a face. We do a happy face. Oh, actually, you're not seeing that for some reason. Let me stop share. Let me reshare that again. All right, so he first rolled a dice and he got a 6, and then he flipped a coin and the coin landed up on heads. So does the fact that when he rolled the die he got a 6, did that affect the probability of him getting that the coin landed on heads?
No.
No. So for this one will be considered independent. Because the probability that he rolled a 6 is still 1 out of 6. But then once he flipped the coin, the probability that the coin land on head is still going to be 1 out of 2. So that event of rolling a die didn't affect the probability or didn't affect the event of getting a heads when he flipped the coin. All right. So that's it for that first one. So let's do the second one. So the second one says your teacher chooses one student to lead a group and then chooses another student to lead another group. All right, so let's imagine that we have a class. And let's say this class only has 6 people. This is a very small class. So let's say we're choosing group number 1. And then we're choosing group number 2. All right, so if I'm choosing a leader for group number 1, if I have 6 choices, what's the probability that somebody will get picked to be the leader? So we got the 1 right.
1 6.
Yeah, 1 out of 6. So the thing is, since we have 6 total students, and only one of them is actually going to get chosen, so that way it will be 1 out of 6. Any question like group number 1, the probability will be 1 out of 6? All right, so say if we pick this guy over here, and that's our leader. So he's the leader or she's the leader of group number 1. So now we want to find a leader for group number 2. So once again, we're only going to pick one leader. But now, how many people do I have to choose from? Cool, thanks, Victor. So 1 out of 5. So we'll say we'll pick this person as the leader. So if you kind of notice for this one, the probability changed from group number 1 all the way to group number 2. Because in group number 1, the probability of me choosing a person for the leader was 1 out of 6. But this once I started choosing the leader for group number 2, the probability changed to 1 out of 5. So this one, the first event affected the probability of the second event. So since it did affect it, this is what you call dependent events. Because depending on what happened on the first event is going to influence the probability of the second event occurring. All right. Any question for that second one? All right, so let's do this third one. So let's see if I could draw a cell phone. All right. So that's your dad's cell phone. And then here's your calculator. So for this problem, yes, apparently the Android. So for this one, it said the battery in your cell phone is dead and the battery in your calculator are dead. So the fact that my cell phone is dead, did that affect the probability that my cell phone battery, well, sorry, the probability, the event that my cell phone is dead, did that affect the probability that my calculator will be dead? No. So since it doesn't affect it, we're gonna say they're independent event. And that'll be it for that one. Any question for that last one? All right, so let's do the last one. So the last one said your favorite color is blue and your friend's favorite hobby is fishing. So that's your favorite friend, favorite color is blue. And then your favorite hobby for your friend is fishing. So for this one, if your favorite color is blue and your friend's favorite hobby is fishing, does one event influence the other event from occurring? So just because your favorite color is blue, does that make it more likely that your favorite, well, your friend's favorite hobby is fishing? No. So for this one, we're gonna say that the events are independent from each other. And that's it. So that's how you want to kind of think about it when you're looking to see if they're independent or dependent. You want to see, does the first event influence the likelihood that the second event will occur? All right. So up next, we're going to get into the multiplication rule. So for this multiplication rule, you use this multiplication rule if you're doing multiple selection. So for this one, we're going to be using it if we're making two selections. So if we make two selections, that's how you know you want to do the multiplication rule, because your events have to be independent and they have to tell you that we want to randomly pick two objects or we want to randomly select two persons. So if you know the events are independent and if you're randomly selecting two people or two objects, you want to use this formula. So the formula says we get the probability of A and B is equal to the probability of A times the probability of B. So one thing you kind of have to know, when it says probability of A and B, it's saying the probability that the first event is A and then the second event is B. So when we say A and B, it means we're doing multiple selections. So we're saying, what's the probability that A occur in the first attempt? And what's the probability that B occur in the second attempt? Any question in regard to that so far? Okay, so before we actually do an example, I'm going to give you why this worked with something that we already have done. So say we flipped a coin 2 times. So I flip a coin 2 times, and what I want to do, I want to list out the sample space. So we want to say the sample space. So the sample space will be heads, 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 tail, tail, heads, and then tail, tail. So that's your sample space of all of the outcome that could occur. You could get heads, 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 tail, tail, heads, tail, tail. So say if I want to find the probability that we get heads, heads, or sorry. So I want to find the probability the first one is heads and the second one is heads. So by looking at my sample space, what will be the probability that the first one will land on heads and the second one will land on heads? Well, if you look at the sample space, how many of those sample space give me heads, heads?
Oh, 1/4.
Yeah, one, because there's only one out of the 4. So you put 1 out of 4. But you could also use the multiplication rule for this one. Because if you look at it, if I want to find the probability the first one is heads and the second one is heads, if you look at it for this one, you could assume they're independent because one flip won't influence the probability of the second flip. So we could just find the probability the first one is heads times the probability the second one is heads. So in this one, the probability that a coin will land on heads is 1 out of 2. And the probability the coin will land on heads is also 1 out of 2. So if you get 1 out of 2 times 1 out of 2, you get 1 out of 4, which is exactly what we got here. So that's how the multiplication rule for independent event came about. So instead of you having to worry about the sample space and then based off of the sample space determining how many of those events meet your criteria, all you have to do is multiply those probability. So let's go ahead and do this first problem. So for this one, it says if the probability that person A will be alive in 20 years is 0.70 or 0.7, and the probability that person B will be alive in 20 years is 0.5. So for part A, it says, is person A independent from person B? So does the fact that in 20 years, person A is still alive, does that mean that it make it more likely or less likely that person B will not be alive or be alive in 20 years? Yeah, so no. So we're going to say no, or sorry. We're going to say yes, these events are independent. And that's it for A. So let's do B. So for B, if you look at it, it says, what are the probability that they will both be alive in 20 years? So we want them both to be alive. So we're going to say alive. And we want person A to be alive in 20 years. And we want alive. And we want person B to be alive in 20 years. So for this one, all we have to do is get the individual probability for both of these persons and just multiply them. So the probability that person A will be alive in 20 years is 0.70. The probability that person B will be alive in 20 years is 0.50. So if you do 0.70 times 0.50, you get 0.35 or 35%. And that's it for B. Any question in regard to B? All right, so let's scroll on down and let's get to the last page. All right, so for this one, it said the probability that randomly selected male age 60-year-old will survive the year is 92.186%, according to the National Vital Statistics Report. So for part A, it says, what is the probability that 2 randomly selected 60-year-old male will survive the year? So for part A, how many people are we randomly selecting?
Two.
Yeah, 2. So if you look right here, it says 2 randomly selected. So for this one, if you look at it, they're telling us we want both of them to be alive in 60 year, or both of them will survive to go from 60 year to 61. So we want the first one to survive, and we want the second one to survive. So we're going to say probability the first one survive multiplied by the probability the second one survive. So the probability the first one survive is 0.92186. The probability the second one survive is 0.92186. So I'm going to go ahead and multiply that. So here, I'll share that on Class Calc. So we'll say 0.92186, and you multiply that by exactly the same thing, 0.92186. And if you look at that, you get 0.8498. Or you could put 84.98%. But that's it for A. Any question in regard to A? All right, so let's do B, and then you're gonna do a problem. So for this one, says, what is the probability that 2 randomly selected 60-year-old male will not survive the year? So for this one, we're kind of doing a little bit different, but it should still be the same process. So we still have the 2 60-year-old male, but instead of them surviving, we don't want them to survive. All right. So the issue is right now I have the probability that they survive. So how can I get the probability that they don't survive? So if I know the probability that they survive, cool. So yeah, so what we want to do, we want to subtract by 100. So if I know the probability that they survive is 0.92186, if I want to find the probability that they don't survive, all we have to do is get 1 minus 0.92186. So let's do that. So if I do 1, oops, if I do 1 minus 0.92186, you get 0.07814. So you want to make sure that you subtract that. You first want to subtract it by 1. So you do 1 minus that, and you get 0.07814. So now I know the probability that they won't survive. So in this case scenario, we want both of them not to survive. So, oops, sorry about that. So we want the first one not to survive. But we also want the second one not to survive. So if we just multiply that out, you should actually get 0.0061. And that's your final answer for that last part. Any question in regard to part B? All right, so what I want you to do, I want you to try this next problem. So take a minute and try figuring out part A and part B. It's exactly what we've been doing. So it shouldn't be anything new. It is stuff that we've been doing for a while. So you do want to use the multiplication rule for this one. So try doing this problem. And if you get stuck or if you need help, yes, either put it in the chat or yes, call out my name. So let's try doing this one. So let's use green since we're doing green eyes. So we want the first baby to have green eyes and we want the second baby to have green eyes. So what's the probability that the first baby have green eyes?
0.06.
Yeah, 0.06, perfect. And the probability the second one will also have green eye, well, it will be the same thing, 0.06 or 0.06. So if you do 0.06 times 0.06, you actually get 0.0036 or 0.36%. All right, and that's it for A. Any question on how to do A? All right, so let's do B. So if you look at the problem, it said the first baby doesn't have green eyes and the second baby have green eyes. So we want the first baby, well, we put not green, and the second baby has to have green eye. So if I want the first baby not to have green eye, what's the percentage that it won't have green eyes? Well, if you kind of think about it, like this should be mutually exclusive because either your baby have green eyes or your baby don't have green eyes. So for this one, if I know 6% of baby have green eyes, if I want to find the probability that they don't have green eyes, you do 1 minus the probability they have green eyes. So you do 1 minus 0.06, which give you 0.94. So you get 0.94. So that's the percentage of baby doesn't have green eye. So then what we want to do, we want to find the percentage of baby that have green eye, which is still 0.06. Any question? I got 0.94 times 0.06. So if you multiply those two out, you should get 0.0564. And that's your final answer. All right. Any question in regard to any of the two parts? Well, you always subtract by 1 if you want to find the complement of it. So if I wanted to find, since I wanted the baby not to have green eye, you subtract by 1. Or if I wanted the person not to survive, you subtract by 1. So yeah, so you could always subtract by 1 as long as you're finding the complement. Any other question? Yeah, you're welcome, Victor. All right, so let me stop the share. We'll